Okay, welcome back to the middle of the other side. The usual disclaimer applies. Anything firearm related is inherently dangerous. Nothing I say here is intended as an authority reference. It's just what I do, and this video was inspired by a friend of mine, Craig, who thought I should explain the importance of case length as it relates to safety and hand loading. And he had said that quite a few people he knowledgeable firearms enthusiasts, didn't quite understand the danger involved in failing to trim the length of the brass. And so I thought about it, and I figured I would make a visual aid to explain that. So all of our cartridge cases that are standardized, they follow certain specs so that the ammo makers can make this piece of brass within certain specs for diameter, length, thickness of rim. All these dimensions are spec'd out. At the same time, firearm manufacturers have to cut the chamber into which this brass, or rather this loaded round, would fit and would be fired from. And so they have to have specs to grind the reamers, to cut the chambers, and to measure headspace. What usually happens with these cases when that's not usually, it happens every time, I should say. There's a lot of pressure in the chamber of the firearm during combustion, and this brass will flow. Just two things are going on as far as the stretching of the brass. The pressure up against the shoulder wants to, and at the base of the bullet that would be in here, wants to push all of that way, right? The pressure inside this vessel is pushing out at every point inside at 90 degrees to the surface. So in the main body here, the pressure would be pushing out that way. On the shoulder, it would be pushing that way. But that vector there has components in that direction and in that direction. I should say that way. It's easier to see. All right. At the same time, this brass is expanding against the chamber wall. So it expands outward and grips the chamber wall. It can only do that where it has enough give. And that stops back here. What happens is this brass will grip the chamber from here forward. And this part back here wants to thrust back against the bolt. is going to thrust back in that direction. And so we'll get some stretching right through here. The brass wants to it's opening up when it fires, like you blow up a balloon. And it's important it is allowed to do that because it needs to release the bullet to go down the barrel. If it can't release the bullet, the pressure will spike. You know, we hear about lately. You hear about this disease and flattening the curve, and it's the same thing with the pressure in a firearm chamber, where you have on the one axis you have pressure going up, and on this axis you have time. So if that pressure spikes, something resists, if there's a resistance to the pressure dropping as the propellant is burning and increasing the pressure, that pressure curve will spike. So it goes sharply up pressure over a small amount of time. This is where, somewhere up here is where your chamber somehow fails. The pressure vessel will fail. When it fails on a firearm, you lose, it either kills you or lose body parts. So to control that, we have the bullet can move forward, increasing the volume of this vessel. As we increase the volume, if you look at the gas laws, increased volume, all other things being held constant, the pressure will reduce. So this curve over the same amount of time becomes less steep. And we don't hit this maximum as fast. And over time, as this vessel becomes larger, the bullet's moving down the barrel that way, the vessel gets bigger while the propellant gases are trying to increase the pressure. The bullet moving forward makes the volume greater and reduces the pressure, so that you get a curve that flattens out, rather than having a spike and then a drop. It goes up and it flattens out, and it goes down over time until the bullet leaves the barrel, and at that point the pressure will drop down to atmospheric pressure level. So avoiding the spike is probably the first main consideration, and it's easy factor to control as far as having brass that can release the bullet. So what I've done here for demonstration, I've made a mock-up, and what it is, or if this is the bullet, this would be our bullet to represent this bullet, and this wire is the neck. So here's the neck section, represents this neck, the shoulder here, and then the body of the case. As if we cut a section through here, just so we can see a two-dimensional representation of what's going on. So we have this, and then we have this. So in a normal, where everything's in spec, in a normal sequence of operation here, we have our round is loaded into this chamber up until about the shoulder area would contact. By the way, this is this drawing is a representation of the chamber inside the firearm, as if we took the barrel and we sectioned the barrel. So we have the main body, we have the shoulder, the neck, and then there's another reduction, another step in the barrel, which is the rifling. So the lands, you see that step from here to here, from here to here. That step is the rifling that will engrave the bullet to cause the spin that we want for stabilization. So we have our mock-up. This round would be loaded, pushed it up into the chamber, and it would contact the shoulder on a bottleneck case like this, bottleneck rimless. The case headspace is on the shoulder. So it's chamber, round is chambered. The round is, when the round is fired, what happens is the pressure in this vessel builds up, and these walls get pulled out this way until they hit the inside wall of the chamber on each side up here in the neck area. That's as far as they can go. So there has to be some allowance for room here. If we look at it again, we have some, I drew it with the dimensions are much smaller in the actual, let me zoom in a little bit here. The gaps are much smaller in the actual firearm, but the idea is that this will open up, this brass will open up this way, right, to go out and seal. It forms a gas seal against the chamber here and here, and gas can't leak back along the outside back towards the shooter. And then this bullet is free to move forward down the barrel, right? That's what we're looking for. So this length from the end of this case here, this case mouth, to the origin of the rifling is the consideration that we have to have when we keep in mind when we trim this case. Because if this becomes too long, what happens is, as we load this round, leave the bullet out of the way for a minute. If this is longer, if this next section on the case is longer, you have a condition where the mouth can touch. It would touch the step here, the transition from the neck diameter to the bullet diameter, and it would get, as it hits those angle surfaces, it gets pushed in, right? If it gets pushed in, that's crimping down. It's like a collet. It gets pushed in this way, and it gets pinched right here. It's pinched right through here. grabs that bullet and holds it. And on certain actions, like a bolt action rifle, where you have you turn that torsional force of closing that bolt handle, it's a long force. It'll move through 90 degrees of rotation on the bolt body, but moving forward a very small amount. It's a lot of force you're capable of applying to this brass to push this case mouth in to grab the bullet. And when you pull the trigger, it doesn't want to release that bullet. It doesn't want to, just like we had before, it doesn't want to open up. It's caught right here. It's caught. It can't open. And it can't freely release that bullet. And that pressure curve, coming back to our pressure curve, we get this spike. This spike can, it can be it can be relieved instantly if your gun blows up. And that's what happens. I don't want to cause anybody any kind of terrible concern, but it's a simple enough thing to have a set of calipers to measure your brass, to know that all the manufacturers, powder makers, bullet makers, they publish literature. There's specs. They call SAMI specs for the case dimensions. So you have a maximum trim length, and what we usually go is 10,000ths of an inch under that max. And if you keep your brass trimmed to that point, it can be shorter, but you trim it to 10,000ths under, and for that firing, you're not going to have any problem whatsoever. But that's the thing. There's something else we're going to talk about. Oh, I was talking about pressure. Also, kind of somewhat related to this concept, because when we load some of our ammo in, you want to get the most performance out of a given cartridge that you can. Typically, what's the point of having a 30-06 if you load it to velocity levels of say like a 30-30? You got a bigger round that does the same thing. So when we're building up our loads, each firearm's an individual. These all these dimensions play in. How freely this will release, how much jump. This bullet has a certain, I didn't show it here, but the bullet will have a certain amount of jump till it hits the rifling, from where it's loaded to where it actually engages in the rifling here. All those things affect this pressure curve, whether it's steep or whether it comes up. It's going to come up fast. It's almost an explosion. It's a really rapid combustion is what happens inside the firearm. So the pressure builds fast, but there are things we can do to, as it's trying to build, we want to turn that pressure into velocity, into a force on this bullet, moving it forward. So one of the other things that we do, when we try to get the optimum velocity we can out of a given cartridge, which involves starting at a minimum powder weight for the charge, and in increasing that charge up until a maximum, where this pressure curve, no matter what we would do, what else we would do, this pressure curve would peak above our failure. This would be our failure pressure, right, for our pressure vessel to burst. So we want to keep our pressure peak below that, with a margin of safety too. But typically adding more powder up until a certain point increases the velocity that we get from the bullet that leaves the barrel. So we can only go so far with that before we have an overpressure situation. So one of the things when we analyze our brass after we fire, if you look here, so here's one of the, let's see if we get this to focus. Here's one of the maybe not. It's going to be a pain, isn't it? Zoom in on it farther away. There we go. Okay. So here's one of the rounds we loaded in the other video. And if you notice here, there's a radius on this primer. From here, there's flat, and then that radius. This can be read in our fired rounds by gauging how much of that radius. Get this one to see if I can get this one to focus. Here we go. So how much of that radius went away, and how wide this flat has gotten, flat on the primer compared to this one. You can see, let's see, you can see how the on-fired brass has a larger radius remaining, and this one is going away, and then you'll have a point where this primer could even fill that remaining gap. It'll fill that gap. It'll really flatten out. I don't know if I have one here that's like that, but what you can do is, I'm pretty sure this was a factory load. I found this range brass. It was on the ground there at the range, so someone fired this and left it there. You safely say that most of the factory ammo should exhibit pressure signs that are safe. So if you look at enough of these factory rounds that have been fired and use that as a guide for your hand loads to judge them by. There's no cratering. Another high pressure sign would be a crater, be like a little raised ridge right around this primered indentation. That's not present here, but what's happening there is that would be the pressure inside this primer when the round is fired is pushing the firing pin back. It's actually pushing the dent it made back out towards the firing pin. and it raises a little ridge around there. Another thing we would look for is around the head there would be a dent. Now that looks like that bend or that flat. Where is that? Right here. That could be where it hit the ground. That could be where it hit the ground, but you gotta watch when you go through your brass. That kind of dent could make a round you wouldn't want to take on a hunting trip, because if it pushed this rim forward enough, if that got oriented in the wrong place relative to the extractor might not be able to get over it because it's too far that way. Another sign we look for is we measure the case head in this area here and here for expansion. Increase in diameter when the case is fired, and there's a spot here where we expect that. We expect that from about here that way. But back here, that expansion is caused by being smashed. So it'd be get there in the frame. It'd be pressing that way, and the head has to go. It has to go out. It has to go this way. Out. So the factory ammo exhibits a certain amount of that. Measuring your own cases with micrometers or calipers will help you determine whether you got a pressure issue. You got to back off on the amount of powder, or something else has to change. Usually it's the amount of powder. But that's it. I hope that helped. Hope that makes that the problem clear as pertains to this issue, especially.